Good morning, this is Professor Grenfell, and today we are going to continue in Chapter 11. This chapter is covering other chi-squared tests, and the first chi-squared test that we're going to consider in Chapter 11, Section 1 is the test for goodness of fit. So this type of test is going to be used when we have a frequency distribution and we want to see if that frequency distribution fits into a certain pattern. Okay, so for example, if you wanted to see that there was a difference in the number of arrests in a certain city for 4 types of crimes, we'll look at a sample of arrests for these different types of crimes, and we'll go ahead and perform a hypothesis test as described in example 11-1. So we have 38 arrests for larceny, we have 50 arrests for property crimes, 28 arrests for drug use, and 44 arrests for driving under the influence. And if we want to say that there's a difference between these categories, then we're simply going to be assuming that each of these categories has the same number, and that is the frequency distribution that we are expecting. For this particular question, we're trying to determine if there's any difference between these. So the expected frequency distribution that we have in mind is that there's no difference, that all of the expected frequencies are the same. And so in order to come up with the expected frequencies, we're going to take the total number of pieces of data in the sample and divide by the number of categories that we have. So in this case, we have 160 sample arrests, and we have 4 different categories for these 4 types of crimes. And so that reduces down to 40. If there's no difference in terms of the population, and this is just the sample that we have that we're looking at. So this is our observed frequency distribution, and in the expected frequency distribution, we'd expect that there is no difference. So 40 would be the expected value for each of these. Okay, and we'll move down to example 11-1. There's a little procedure table. We'll go back over it. Example 11-1 on arrests for crimes reads as follows. Is there enough evidence to reject the claim that the number of arrests for each category of crimes is the same? Use alpha equals 0.05. So let's review the procedure table for, well, this is basically the same as for any hypothesis test. We're going to first state the hypotheses and identify the claim, then find the critical value. In this case, this is a chi-squared test, so we're using table G, and this is always a right-tailed test. Then, in step 3, we compute the test value. The way that we do this is chi-squared, oh, not chi-bar, chi-squared is equal to the sum of all of the observed values minus their expected value, whole thing squared, all divided by E. So we take all of these values and add them all up. Then we will make the decision and summarize the results. So for this particular problem, our hypotheses would be H subscript 0, there is no difference in the number of arrests for each type of crime, and that's the claim that we're going to see if we can reject. And H subscript 1 is there is a difference in the number of arrests for each type of crime. So that was step 1, to state the hypotheses and, well, not so critical, identify the claim if possible. And then step 2, we're going to find the critical chi-squared value, so chi-squared subscript alpha, using Here, k minus 1 is equal to 3, so we have 4 different categories, so the degrees of freedom are 3, and we have alpha equals 0.05. So the critical chi-squared value there, looking it up in table G, is 7.815. So here's a quick sketch of our chi-squared distribution curve, and 0 is there. Our critical value is 7.815. So the shaded region is the critical region or the rejection region. It has area 0.05. And if our test statistic lands in this region here, we would say reject the null hypothesis and say that there is evidence to suggest that there is a difference for the number of arrests in each type of crime. And if not, if our test value is in this region here, then we would say, well, we can't reject the null hypothesis, so we're not seeing any difference in the number of arrests for each type of crime. In step 3, we have to compute the test value, or the test statistic. And so I've made a little table for the 4 different categories: larceny, property crimes, drug use, and DUI. And we're going to write down the data that we have. So there were 38 arrests for larceny thefts, 50 arrests for property crimes, 28 arrests for drug use, and 44 arrests for DUI. If there's no difference, then the expected frequencies are just going to be 40 in each category. So there were 160 arrests total. Dividing that by 4 gives us a uniform distribution, no difference between larceny thefts, property crimes, drug use, and DUIs. And so each of those we would expect just 40. Now what I've done here, I didn't leave myself very much room, but I've gone ahead and subtracted the observed value minus the expected value for each one of these categories. So there were 38 actual arrests and we expected 40, so the difference would be 38 minus 40 is -2, and so on and so forth. We've done this for all of these. Now I better give myself a little bit more room. Just go ahead and erase that. Maybe come back and redraw it later. What we have to do is we have to square each one of these values. So we have to do O minus E whole thing squared. And then, well, here it doesn't really matter, but we have to divide by the expected number. I say it doesn't really matter because it's always going to be 40. So we could just divide the whole sum by 40 at the end. So this first one is going to be -2 squared over 40. This next one is going to be 10 squared over 40. So see, they're all over 40, right? -12 squared divided by 40, and 4 squared divided by 40 as well. We compute chi-squared by taking the sum of all of these values. So I'm just going to say plus signs in between. And in this one, we got to be a little bit sloppy. See, I just added up all of the numerators, got 264. And then since they're all divided by 40, the common denominator in all of those is 40. So I could just do that division at the end. But in other instances, we got to be a little bit more careful because the expected values in our expected frequency distribution might be different. Okay. Here our test value comes out as 6.6. So that was step 3. Jump to the next page. Step 4 is we're going to make the decision. So here I'll re-sketch the chi-squared curve. I'll say what the critical value was. It was 7.815, I believe. Shade in the critical region. And where was our test value? Well, I didn't measure this precisely, but 6.6 is on the left side of 7.815. So we're not in the critical region. therefore, or not in the rejection region, so therefore we cannot reject the null hypothesis. Don't reject the null hypothesis. And then finally, step 5 is we summarize the results. So we didn't reject the null hypothesis, so there is not enough evidence to reject that claim that there was no difference in the number of arrests for each type of crime. That verbal expression had way too many double negatives in there, so I'll just say there was not enough evidence to conclude that there is a difference in the number of arrests for each type of crime in this particular case. So just to kind of go back and re-examine the conclusion here, if there's no difference, we would be expecting 40 in each category. And even though it looks like the property crimes are disproportionately high in this sample, the drug use crimes, or arrests, I should say, are a little bit lower than what we think they should be. Statistically speaking, there's not enough evidence to say that they're outside of this expectation, or in other words, it's a pretty good fit for this frequency distribution where they're all uniform, they're all the same. So that concludes example 11-1, and in the next video we'll see another application of the chi-squared test for goodness of fit.